你们是用我的连结加进来的吗 ？Hello，
好像我应该是用点，
用点的就好啦。为什么不行呢？不是一样吗？我看一下我什么地方，我看一下我什么地方要把它们加回来。Hold on, give me a minute. I try to add them on. I didn't see their requests. I don't know. 团队新增新人。Hold on， 老师。Hold on。
小弟，那我看到我上班地方了。
Hold on。
我送到我上班的地方。
好，
拜拜。
拜。
Yeah, you give me your student ID and I can add you on.
It has to microphone.
See. I cannot find you. Okay, hold on. Actually add you on.
老师都进来了，
怎么回事啊？不知道。OK, sure. 那你刚送什么不一样的给他？他为什么不？你是送？
我是直接从那个成员里面，然后反正就是我也是发
什么？
连结啊，就是分享邀请，然后我是复制这个会议的。
Okay, however, okay, sure. Yeah, hold on. I think everybody is back here, and so going to share the slide and hold on. Yeah, give me a minute. 你要帮忙录音哦。
哦，我已经在录影了，
Okay, sure. Okay, thank you. So course material, and we have TQM. So last time we still in Six Sigma, right? Okay. So think, can you see the screen?
Yes, teacher.
Yeah, I think no, I need to get it larger. I need to get. Is that better? Okay, so let's get started. We have last time where we're getting at. We're getting at MSE. Which page are we getting on? The baseline. Not this one. Yeah, we have done this, right? The outside, the noises, potentials, the common causes, gauge. We mentioned this before, right? Did we?
Yes.
Okay, so it's this page we're getting on, right? We're getting at. So map the process. So map that means, okay. So please also open your text dialog box. So this is the mapping the process. Try to characterize the process. The characterize process, that means we know we need to understand the interrelationship between the x and the y's So actually, we always ask several questions. What problem happened and how it happened and why it happened and when it happens. So typically, we we ask this kind of question, try to identify what kind of problem we try to solve. Then second, and identify the variables. So this is a potential. The causes. So typically we call it is the control variable. Control variables. So then we like to measure the process. Measure the process, that means we need to get the response. Get the response, that means so based upon the CTQ. The CTQ is critical to quality. So what is the most important? The up to most important to the output. So that is related to quality. What is influential effect on the response? And the response got to be linked to the CTQ. So then we're going to make the measurement. You see the text box I type, can you?
Yes.
Okay, so
Yes, teacher.
And then you can use a copy and paste as a class note and for your personal perusal. So to understand where you want to be, you need to know how to get those x. So sometimes the x, this is a bounded. This is a bounded number of x's. So this is very difficult to try to identify what is the most important. What is this moderate, more important, less as important. So I think this is a key job we try to achieve. So we use, yeah, typically we use the Ishikawa. We use Ishikawa to identify the process, the possible causes. This is like a man, machine, material, method, and the environment. Yeah, this is old-fashioned. This is really old-fashioned. And then we advance to the moderate methodology. No, this is a little bit more advanced methodology. We just screening experiment from DOE. The DOE stands for the design of experiment. And so like to advance, use the most advanced, the advances of new technology. So we try to just install the sensor to perform the feature engineering. So I think that will be the most advanced state of the art. So the feature engineering can be classified. The feature selection, the feature creation, and the feature extraction. So this is typically employed by the data scientist. Then there's one more thing I like to share with this. We call the Ishikawa. Ishikawa. So typically we use a qualitative methodology for analyzing what is a possible root causes. So this is kind of old-fashioned. We like to add more. So like called I. I means this is intelligent. Intelligent added Ishikawa. So that is quite straightforward. How can we add intelligence into that? I mean, we like to just collect the data. Then every time we perform the Ishikawa cause and effect diagnosis, we try to just bring some evidence. What is the frequency? What is the relationship? What is modeling the modeling result? What is called the feature? I'm sorry, feature importance. To be accompanied Ishikawa. So this is quite clever. I think this is a new one. I just cranked it out just a couple months ago. So I called the Ishikawa. I haven't published this idea yet. So the Ishikawa, the intelligent added. So every time there's a fish bone, we have a big bone, we have a moderate bone, we have a small bone. For each bone, there comes with the evidence. The evidence comes with the data. The data comes with the weight or importance of the variable. So how can we go to get those data? So we install the sensor to the equipment. We install the sensor to the tooling. We install the sensor to the operator. We install the sensor to the environment facility. So we collect all the possible data. Then by feature engineering, those important related to the response variable, the response related to the critical to quality, the quality related to the yield rate, or cost, or the benefit, or the profit. So can be quantified. So, and that's why we call it Ishikawa. And it can also come with the Pareto process, right? Then we use the 80-20 principle to give a cutoff criteria. Then so I think the 80-20 Pareto going to be the first. So the Pareto analysis can be used as the first cut. I'm sorry. So Pareto analysis can be used as the first cut. So going to just screen those. Using. Is there any question? Hello. Okay. So first cut and screen those insignificant ones, and then use a feature engineering, or called a feature importance as the second cut. Yeah, this is quite clever. I think it is a durable and which is also feasible. And so eventually, then to understand where you want to be, then we're going to so if some of you like to use the Taguchi's method, yeah, that's fine. Since the Taguchi method, which consists of the system design and the robust parameter design and tolerance design, right? So in here we focus on robust parameter design. So So those a number or those data or those information can be as an input for the Takeuchi method to perform the robust parameter design or the RPD to put those data into the inner array for the controllable variable, for the outer array for uncontrollable variable. So that can separate something. This is very easy to vary something for the process engineering or data sciences. Very difficult to vary. Then finally can use the signal to noise ratio. To quantify, so what kind of level of the factor can be set up or determined in order to get the best robust parameter setting, with which we would like to have the better result. So there's the three cases. The three most important cases in the robust parameter design. So I mentioned several times in my class, like a target is the best. Have you remember? So, do you remember? The target is the best, right?
Yeah, yes.
And can you just give me what the other two? Somebody who can help me? How about the other two cases? So,
I'm thinking.
Or Patricia like to help, or Dujano like to help? So the minimum is better, right? The maximum is better, right? Told you about three different cases. So have you recapitulated? Okay, then we move on. So then now we are in the process moving to the stage of the evaluate. So we understand the process. So take the measurement, we like to evaluate how can we understand the process. So we call the process characterization. And then once we have a basic understanding of the process, then we try to improve and verify the process and maintain the process. This is how this is a working loop for the Six Sigma. Okay, then in many cases, the process capability. So we mentioned. So would some of you like to share what is the process capability? So what is the process capability? Some of you like to. Yeah, no, this is okay. So what is the process capability? Will any one of you would like to share your idea with us? Meng, you would like to share with us?
Sorry, I don't know. It's
Okay, process capability we introduced. So process capability, that means so when we like to to accept the order, would like to manufacturing the product for our for our customer. So customer going to have a specification. So the process capability that is used to determine are we capable enough of accept the manufacturing order from our customer? Are we able to make the quality qualify a product for our customer? So there's 3 different types we like to measure ourselves to be capable or not. So this is the potential capability. We have actual capability and the Takeuchi capability. Have we mentioned these 3 in class? Yeah, 地伟、梦雨。
Yes.
Yes, we have a 3 question, right? So we have a potential capability called the CP. So we have an actual capability called the CPK. Then we have a Takeuchi capability CPM. Do I remind you?
Yes.
Okay, thank you. So look at the graph. So look at the graph. You can see that the process capability. Then this is the spec. This is the upper specification limit, lower spec. So that means this distribution. So this our process not center. So going to move. Can you see my mouse moving? No. Sorry.
No.
No. Okay. So okay. I need to change. Okay, I need to change the other way of presentation. Hold on. I need to. Yeah. Okay. So how can I? Hold on. Let me use a different way. Hold on. Okay, I try to use this way. Okay. I think that'd be better and the easier way for visualization like this. Okay, then hold on. I'm back. Okay. Can you see the screen yet? I think you do, right? Can you see the mouse?
Yes, teacher.
Yes.
Okay, cool.
Yes.
Yeah, I think that's better. I think this is better. Okay. So I'm going to toggle 林继伟. Okay. Who is 林继伟? Okay. Okay, I toggle back to the slide. Okay, so what is the problem of this process? Somebody? Yeah, Patricia? So this is, so you can see the CPK is quite low. The point 51 is quite low. The lower specification limit and the upper specification limit, yeah, upper. So you can see that it is so the process not center, right? So going to move going to adjust the center of the process toward to the right in order to fall within the limit, right? Then what is the problem of the process on the right? The standard deviation is way too high. So going to reduce the standard deviation. So let me type in then. So the process on the right, no, on the left, I'm sorry. The problem is we try to bring or move the process to the right. So the process on the right, so we try to reduce the process variability. So different process have their different problems. So let's toggle back to the slide. So in many cases, the data sample can be transformed so that I can approximate normal. So why normal is important? Why? Gentlemen, why normal is important? So like this, we do the log transformation. Since the data, it doesn't follow the normal distribution. So this is quite key to the statistical application in practice. So typically do the transformation. So why we do that? Since the transformation to normality helps data scientists analysis and conclusion making. So this is quite important. So this is based on statistical theorem. And for example, square root or logarithm or reciprocal often make the positive skew distribution like this one converted to some close to the bell shape. Like this is a skew, this is a right skew distribution, right? So typically we use a square root or logarithm or reciprocal to make it into the bell shape like this. So you can see the normal probability plot like this. This is quite deviate. They're quite remote from the normal distribution after transformation. Yeah, it performed better and close to the normal distribution we expect. Okay, then we'd like to mention, so what do we do and what do we need? So there's several things we'd like to mention. The first one, the off target, like this. This is the upper specification limit and the lower specification limit. And this is the center. So you can see that the distribution with a quite limited variability. And what is the problem with this process? Somebody?
Bias?
Yeah, this is not center. That means the process should put to the left, should totally push to the left, right? Since you can see that with respect to the bullseye, do you see the breakdowns? The breakdown is our output of the process, so they are not center. Even though they are packed together with a very limited region on the target. However, they are not on the bullseye. So the best we can do, we just move the distribution on the whole and toward to the center, that is a bullseye. So off target and the low variation help potential defect, and it's good. So which is good CP and but really bad CPK. So high potential defect like this one. And then we look at the second. What is the problem of the process? Gentlemen, ladies? Mengyu.
It separates too many places, not in the center.
Yeah, that means we have too large standard deviation, too large variances like this. So yeah, this is our target, right? However, most of the output, this separates totally in different direction, in different places, so widespread. So we try to reduce that, try to reduce the variability. We also like to center, also like to reduce the dispersion. So we call it dispersion, data dispersion. So that is high potential defect as well, like here and here, and not so good CP and not so good CPK. So we see the drawback of these two processes. So after correction or after assignable causes removal, then we like to bring the process back to here. This is really packed in the center and with a quite limited variability. So variation reduction and the process centering create a process with a less potential for defect, like this one. The concept of the defect reduction applied to all processes, not just manufacturing. Like a McDonald's, when you buying the ticket from the Easy Fry, or you go to the university counter for the semester registration, or you go to the IEN department applying the master degree, 5+1 program, and so on and so forth. They're all related to the process or operation improvement. So it is not only limited to the manufacturing practice. So move to the next one. So eliminate trivial many. So this is screen. So create a screen now. So that's why I mentioned use the 80-20 for the first cut. You use a qualitative evaluation based upon the domain center, called the domain center. Or the domain centric. So technical expertise use the domain knowledge to remove those trivial many, and also graphical method. Graphical method that's called the Pareto chart. Then last one was screening design experiment we mentioned already, and identify vital field. So use a Pareto, and so hypothesis testing or ANOVA, called ANOVA, analysis of variance. Yeah, it's known as ANOVA in statistical analysis. Is quite useful. Then finally, we quantify the opportunity for improvement. Then that is linked with a link to the reduction in variation and cost and benefit analysis. Finally, our goal identify the key factor. This is X, or typical in semiconductor manufacturing, which is also known as the key parameters and the key processing steps. Yeah, in semiconductor. Semiconductor manufacturing. Okay, then. So, yeah, there's another tool called the box plot. So there's this is a three basic element that collected to form the box and whisker plot. So which is called box and whisker plot. Okay, box and whisker, and so you can see that without X value, so now it doesn't show, it only shows the distribution. This is not, it doesn't show specific range of the X. So you can see that this is the range from the lowest to from the smallest to the largest. And so in the graph, there's a buck plot, and the graph also buck plot that can be separate into the, so the shift operator or they can, according to their different category, for this Monday, Tuesday, Wednesday, Thursday for operator, for John, for Yu, for Shao, for me, and so on and so forth. So that can use to judge the capability and the performance for each operator and shift, like a day shift and night shift, or this is the first shift, second shift, or third shift. It depends. So the separate in different shifts for performance analysis. So there's a couple things I'd like to mention. We first need to rank all the data from smallest to largest, and in the middle, you're going to cover 50%. So you can see the bottom, the edge of the bottom of the box. It is a Q1, which accommodate 25%. This is Q1. In between, it covers 50%. So upper edge of the box, that's called a Q3. So Q3 minus Q1, this cover 50%. So this is this position is identified as Q3. This position is identified as Q1. So there's a horizontal bar. The yellow bar represents 50%, that is a median. And then there's a whisker on the top. There's a maximum and the minimum. So there's a maximum, median, and a minimum. Okay, then statistical analysis. So apply the statistical to validate action and improvement. Yeah, let me just enlarge the illustration. So compare the sample mean and variances. So hypothesis testing, this is a before, maybe this is a after, maybe this is method A, this is a method B, maybe this is by machine A, machine B, assembly line A, assembly line B, or the operator A or operator B apply statistics to validate action. So we do some action. Does it really make significant improvement or not? So do the hypothesis testing, collect the data, and perform the statistical analysis to compare the two populations to see if there is a significance or not. So called hypothesis testing. There's a this is an H norm. I'm sorry. H norm versus the HA. H norm, this is known as the null hypothesis. And HA, this is known as the alternative hypothesis. Typically, we're going to also alpha. We use the alpha, that is use the level of significance. Typically, the level of significance. So that means this is a type 1 error, like a COVID-19. COVID-19. That means what is called the type 1? I'm sorry, type 1 error. Type 1 error, we also known as alpha. COVID-19 or data science, there's also called a false positive. False positive rate, that means, for example, somebody, a civilian, actually, which is not infected with COVID-19. However, he go to the test, to the PCR test or the quick screen. However, the test is positive. So actually, who is not infected. So this is called a false positive, right? So in Chinese, we call it the 假阳性, right? This is a false positive rate. False positive rate. So if you go to PCR or quick screen, however, the result is positive, actually, which is not true. Actually, you are not infected. The false positive. Typically, in the manufacturing, with the positive, we use a false positive. No, the alpha, the level of the alpha we typically use is 1% or 5% or 10%. This is the most three more frequently used levels of the significance in practice. Is there any question? Mengyu? Hello?
Hello. No question.
Okay, thank you. So we go back to the slide, and then we also do the regression. So somebody to answer me, what is the regression for? Why do we need to perform regression analysis? Why do we? Somebody? Yeah, Carl. So wow, I know. Yeah, so Lin Zhang. Okay. Lin Jiwei. Who is Lin Jiwei? Is Lin Jiwei here?
Yes.
Okay, we'd like to say something about why do we need perform regression?
To predict.
Yeah, that's cool. That's cool. You say the keyword. Thank you. So that is, yeah, that's cool. That's cool. Prediction, forecasting, cool. Prediction, forecast. Thank you. Enjoy it. So appreciate it. So back to here, is factor really important? So yeah. Identify relationship. This is input and output relationship. This is the regression really fit to the data. Actually, we don't know yet. So regression can be classified for different types. For example, we have a linear regression, we have a nonlinear regression. Nonlinear regression. We have a logistic regression with so many. And we can also be called the GON. So GON as known as the general linear model, or somebody is called a general linearized model. Okay, so it's quite versatile. That can be used to describe how the data fit to how the model fit to the data. So is a factor really important? So actually, does it show any pattern? Do we understand the impact of a factor, identify relationship, and also the stability limit? Do you see the upper limit and lower limit? Then we can construct the confidence band. Prediction. This is really important. Or this is a confidence interval. The confidence interval, or it can be the prediction interval. Yeah, that's a quite useful in practice for the user or process engineering to see, since sometimes the data is subject to the sampling, the error. So you need to build a confidence region if it falls within a tolerable or the acceptable region and it passes. So there's no absolutely threshold or cutoff criteria to increase the type 1 error. Okay, then we have a 10 minutes break. Remember to return to the online class after 10 minutes break. I see you later. Okay, we're back to the class.
Teacher.
Yes, we're back to class.
Teacher.
Yes.
I can see the chat channel. Maybe you need to add me to the team member.
You can. Okay, so team member. Let me see how can I add you. So I should add you here. Hold on. Could you give me your ID number? T.
107.
107.
370134.
34.
Nalis.
Hold on. How can I add you this? Okay, give me your Chinese name. Do you have Chinese name?
林继伟。
季是哪个季？
The third. No. 7.
伟 OK.
Yeah.
伟是哪个伟？
5.
Right.
Please.
Okay. Okay, so you are on. You are in the team now.
No.
Can you see the text? No.
No.
No, you need to push. There's a upper right. There's a.
Yeah. But I can use this.
Why?
Don't. It can be used.
Cannot be used. How come? Can you see the screen now?
I can see the screen, but I can use the chat channel. I can see the chat channel content.
You cannot see the chat channel.
Yeah.
It's gotta be. Okay, let me see that. How can I? Chat channel. Okay, let me see. Would like to. Okay, so let me see. Lin Jiwei, you are in the team now.
But I can use this. Maybe I reconnect.
Yeah, you reconnect. You just log out and reconnect once again. Try.
Okay.
Try. Okay, we wait for Mr. Lin a little bit. So CDC just announced we have almost 300 infection cases today added. Additional 300 cases. Yeah, I think for Taiwan it's okay. Now the most urgent thing for Taiwan is try to acquire enough vaccines. I think that is the most urgent. Yeah, you can see that. Yeah, that's how. Okay, Jiwei, you are on. Okay. Okay, back to here. This is a plot. Yeah, this is a tool plot for the Six Sigma. Let me just put it just enlarge it a little bit. So this is a poor to good. The ZST. This is the this shift. This is good. As small as possible. This is a good. SD for the short term. Short term the Z score called the short term this score. The short term this score, that means short term, that means we only sampling perform the within sample variability. Yeah, let's see them. Let's see. Any question? Okay, sure. Okay, then we get it. So SD, if we have a larger the standard deviation, that means better. So we have a smaller shift, the process is better. So D will be the best. The A is a poor control. improve process. So the control related to the horizontal, the vertical axis, the performance of process, it is related to the horizontal. So B, that means must control the process better. So we try to lower. So going to reduce the shift and to bring the B process back to D in this way. The C, say process control is good, however, bad process of technology. That means we don't have a capability is no good, however, control is good. So this is about the control, this is about the technology. So the capability is no good. The D is the best. We call the world class or call the best practice. For the best. Or somebody call the benchmark. Okay, then we move to the next one. So Six Sigma design process, so consumer Q. So always there's consumer, the voice of consumer. So provide technical requirement, preliminary drawing, what is the plots of the mechanism, mechanical design, or what is the specification that's stored in the databases, and identify the critical to quality. So what is the KPI? What kind of objective you like to achieve? So based upon the Q from the customer, then we proceed to the identify the critical process. We process which part or which station or which process most related to the CTQ. Then going further, obtain the data in the similar process. Then calculate the Z. Z is this one, the Z short term. So how many process capability of the short term? We calculate the Z score, a Z value, and then we're going to feedback the revision 0 drawing. So is any possible opportunities for improvement? So if this is true, then we're going. If this is not satisfactory, going back to obtain the data once again. Then so calculate the Z score if not Z is not big enough. Then we're going. So we need to stop here and adjust the process and the design. Go back again. This is the looping for improvement. Then if it is done, then going to the next stage. The piece inspection. This is called the prototyping. Prototyping process. Then going to the pre-pilot data. So before ramp up. Before ramp up. Yeah, before ramp up. Okay, then before ramp up, then pilot data. So we obtain the data, then we're going to check in the Z level. Since in the design phase, we already have a sufficient Z score. Then there's a pilot study, we get the data. We need to confirm and validate the Z value, Z level can be regenerated in the pilot. ZSD be regenerated in pilot study. Regenerating pilot study. So check if this is less than 3. 3 is a totally quite low standard. So need to stop and fix process redesign once again, like the design phase. If this is greater than the design intent, DMAIC, then they're going next, going to the next one, the design phase. This is a pilot study, DMA, and improvement. So going to improvement process. So another concept we call the QFD, FEMA. So the first of all, like to define the customer queue and technical requirement we need to satisfy. So the customer queue is the block cannot rattle, must not interfere with box. So must fit exactly on the position. So technical requirement, there must be a positive gap. That means we need to have a tolerance. So we need to have a tolerance for manufacturability. Tolerance for manufacturability. So need to have a tolerance. So define the customer queue need its own standpoint. Then later, this following 3 technical requirement must be a positive gap to have an allowance to fit it into the entire frame. So typically, how can we know the queue from the customer, the quality, the QFD? This is quality function. So it's called the QFD. Then what is a FEMA? The FEMA, that means is a failure mode. So we try to avoid. Avoid failure mode as much as can be. So this is our objective. Then we have a failure mode. Failure mode. And the failure mode, that can be reduced to the effect. What kind of effect is going to happen? Then the failure mode is going to have a different effect, maybe on the people, maybe on the process ill, or it can be the performance, or to bring us so many breakdown. Then, so what is the possible causes? So that is failure mode, and can be decomposed in the or linked to the effect. And later, I would like to relate it to the possible causes. Okay. Like this. This is a FEMA. Let me just print it out. FMEA. Okay, let me just bring you some sources from the wiki called FEMA. Like to use a wiki. Okay, which called the failure mode effects analysis, also known as the FEMA. And failure mode in plurals, typically use put in the FEMA, although read the failure modes. And a few different types of FEMA analysis exist, such as functional FEMA, design FEMA, or process FEMA. So, so it can be extended not FECA, the failure mode effect and criticality analysis, or there's an inductive reasoning for logical analysis, signal point of the failure. So let me see that there's something like to mention. Hold on. Let me see that. Okay, the first example of FEMA, so the probability severe. So there's some point we call the risk level, PSD. So example of the FEMA, basic term. Okay, So there's an action, the priority. So called the RPN. This is a risk priority number. So the risk priority number in AIAG and FEMAR that published in the handbook of 2019. The failure, that means loss of function under state condition. Then we have a failure effect. Hold on. Then there's an effect. The RPN, risk priority number, that is defined as the modification of the severity number of event. How severe it going to bring to the process, bring to the organization, bring to the department, and the probability, how often it occurs, how often it is taking place of the event occurring, and detectability, or is that easy to be detected or very difficult to be detected, or we're going to spend some effort, or we're going to invest the high tech for detection. So that is probability that event would not be detected before the user was aware of it. So the RPN defined as the modification of the severity times the probability times detectability. Okay. Okay, so yeah, this is the table example of the FEMA. The example of FEMA, the worksheet. Okay, so I'll stop here and okay, I give you the link right here. Okay, this is the FEMA. Yeah, cool. Then next one. So second, so define the target dimension. So target, this new design. So yeah, or the process mean existing design for all the mating part. So yeah, is that really we just adjust the target or nominal value in order to satisfy the, now, first of all, you need to satisfy the customer queue, then to let the manufacturing team that is able to produce those products with the quality without undue difficulty. So that is called a nominal value. Somebody call the target value, or somebody call the set point. Set point. So in mechanical engineering, we call it a set point. So define there's a gap. This is so the gap must be something like that. So, okay, then the number 3, gather process capability data for each one. So for each way of a tolerance, then use the actual and similar part data to calculate the standard deviation of the largest contribution. So yeah, for each one there's a subject to error. So that standard deviation should be added like a SSA plus SSB plus, SSC equal to the, SS total. Yeah, idea like this, we call the variance decomposition approach, variance decomposition approach. So, and then like this, we have upper and the lower, and this target is only 0.1, so must within this range. So going to add those tolerance together. This is called a plus. So if we have a smaller, then there's a larger tolerance that can be satisfied with the manufacturing team, which also meet the meet the voice of customer or customer queue. So may use expert data for minimum contributor. Do not calculate from the current tolerances. So going to combine them together. Then, okay, then later like this, the gap. The gap is the box, the minus cube 1, minus cube 2, minus cube 3, minus cube 4. So this is the gap right here. So for each one, we have a shorthand. So within the cube, the variability that is known as the sigma shorthand. Then the shorthand, the gap, the 5.080 minus the Q1, Q2, Q3, Q4, the 0.16 right here. This is a gap. Then the sigma gap, this is a 0.001 square, Q1, Q2, Q3, and Q4. 1, 2, 3, 4, 1, 2, 3, 4 totally, and Q4, 1, 2, 3, 4, 5, and the box. The box should be accommodated. So the sigma gap right here, the 0.00224. So we also calculate the long term, the gap, the sigma gap, since this is a shorthand. So this, then the should be the 0.0015, 0.0015, 0.0015. This number is getting from, let me see that. Where can I get this number? Yeah, let me see that this number, where does this come from? Hold on. 0.001, 0.001, 0.0015, 0.0. Actually, some information is missing. Since 0.015, that means for the long term, that means we produce the block one for batches, for producing the block 2 for batches, not only the individual block. So the variance a little bit larger than that. So this is for within the batch, this is 0.001. Between the batch, this is the 0.015. So this is 0.0035. So going to calculate sigma gap and sigma gap for the short term and the long term. So those information maybe I'm guessing. I make a guess. This will come from the batch of the block 1. So second, this is the second batch of the block 2, block 3, and block 4, and also for the frame, for the box. Okay, so this is how we apply the Six Sigma to the quite straightforward assembly line called the manufacturability so hold on. This is the Six Sigma manufacturability applied to assembly line practice. Yeah, something like that. Okay. Then we have proceed to the improvement phase, improving the verified process. So look at that. So yeah, what do we need to do to improve my game? So improve. So that means we must. Must stay within the current resource management. So that means stay within the current resource management. That means we try to maintain the minimum level of the human resources or task forces or technical support from our R&D and operating support from our manufacturing team in order to make the fine tuning. So it is not saying we try to improve significantly since the prototyping has been done and pilot has been done and some capability, the Z short term, Z long term has been done. The only best we can do, is that possible to make the minor adjustment, minor fine tuning to streamline the production line. STREAM, streamline the production system. So this is the purpose, streamlining. Streamlining. Okay, in Chinese we call it 流线化. To make it smooth. So in translation to English, to how to making it smooth. SMOOT, to making smooth. And then back to here. So where can we improve that? So yeah, maybe the trial and error will be the quite crude implementation. And crude implementation is to use try and error approach. Yeah, this is quite cool implementation that has been quite widely accepted in practice over the past 20 to 30 years, worldwide. So, like this, design of experiment has been, I think, was invented back in 1920 in British. So there's several agriculture researcher or statistician. So they try to estimate effect of the independent variable on responses. They try to use a different, use the design experiment in order to improve the output of the agricultural crop output on a designated plot of the land, then try to use so what is a watering scheme and what is a fertilizer scheme and what is possible way to bring the so what is the level of the sunshine exposed. So then there's a terminology to try to manipulate the possible level of the X in order to improve the output of the Y. So factor. So it is independent variables. The level is a value for the factor. So for example, if we have a factor A, so we have a level 1, level 2, we have level 3, we have level 4, blah, 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 we have level A. For factor B, we have a level A, level 2, level 3, level 4, blah, 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 until B. So simultaneously, consider factor A and B together. So I'd like to ask you how many possible, combination of, of A and B together. So how many possible combination? Lee. Where is the Lee? Lee what? Let me see. Lee Qihong. Yeah. Lee, are you?
Teacher.
Yes.
Yeah.
So how many possible combination of the factor A and factor B together? Can you see the see the text I typing?
Yeah, I can see it. I don't know, teacher.
Okay, so for factor A with A, it's going to be A times B, right? For example, factor A, we have a 3 level. Factor B, we have a 4 level. 3 by 4, going to be the 12. Total 12 different combination levels, right, together, right? Okay, then back to, or toggle back to, this is why is the response. So, yeah, typically try to fine tuning, just tweaking the X a little bit. How to tweak, T-W-E-A-K, tweak the level of X in order to maintain a better output. I'm sorry, output of Y. So that'll be our objective in the face of control, or to maintain a stabler condition on Y. That's it. There's only two things we can think of. How the control can be done. First of all, input the level of the output a little bit, or maintain a better stability. So this is, first one is a consistency. The second is the stability. The first one, consistency, in Chinese we call 一致性. Right? The second, stability, called 稳定性. Okay. So I give you the Chinese translation for your better interpretation and the interpretability. Then back to here, like this. This is a coffee example. Yeah, you understand what I'm talking about. So, in this is how many factors involved in this example? Li Qiwei? Li Qihong, for this, how many factors involved in this example?
And
how many?
3.
Yeah, 3. Bingo, very good. The 3 factor. First one, the coffee brand. What kind of coffee brand? This is a Maxwell. Yeah, this is the chock full of knot. Yeah, the water, different water. We use the spring water or tap water, directly use it from the faucet. The coffee amount, the 1 spoon or 2 spoon, the level. The level, that means we have a 2 level. The brand will have a 2 level. Totally, how many combinations we have, Mr. Lee?
2.
No. Totally, the 3 factors. How many combinations?
9.
9 to 9. Are you sure about that? Would you think of one more time? First factor 2 level, second 2 level, third 2 level. So totally, how many level we have? Mengyu?
27.
27. For 1, this is 2. How many total we have? 2 by 2 by 2. So it's going to be 8,
Oh, 8.
right? It's going to be 8, right? Hold on. Going to be 8. Okay, for each one we have 2 levels. So this is 2 raised to the power 2 raised to the power. Excuse me. 2 raised to the power 3. That is I'm sorry. That is equal to 8. Then back to here. Then this is the main effect. The main effect of each individual factor on responses. So for factor A, the factor B. So we might just send a questionnaire. QUES. We send the questionnaire to our customer. We try the different combo of the coffee brand. Use a different water. There's 1 spoon or 2 spoons of the coffee powder. Then to let our subject for tasting, they responded. Do they feel it? Do you feel how? Do they like it? So we're going to use a Likert scale. Likert scale could be the 5 or 7 level. 7 level. Maybe this is -2. I'm sorry. -2. This is -1. The 0 and +1 and +2. So this is a 5 level. 0 mean okay. I don't feel anything. I don't like it, and no, I neither like it or neither don't like it. I don't have any particular opinion. The -1 that mean I don't like it a little bit. -2 that mean I don't like it very much. The +1 I like it. I tend to like it a little bit. +2 I like it very much. So this is a 5 scale. The 7 scale. No. The Likert 7 scales, that is a -3, -2, -1, 0, and +1, +2, and +3. So this is totally 7 scale. So get the data, get the feedback on the subject. Like this. So, well, the brand B is a better. So actually our customer like the brand B more than the brand A. So this is called the main effect. Effect of each individual factor on responses, on the response. So concepts, so this is 3 major, main effect. So for, let me see that. This is the, hold on, let me see that. So this is, okay, coffee brand. The red one is coffee brand. And the black one is the, let me see that. This is temperature, temp X and Y. No, we don't have an X and Y. Coffee brand water, maybe water. Okay, however. Then third one, no, it doesn't show. Okay, the third one, taste. Okay, this is 3 different main, maybe water. So yeah, for these 2, we're going to have an interaction since these 2 lines, these 2 segments are not parallel. 2 segments are not parallel. I'm sorry, LEL, not parallel. Let me explain this way. Let me see that. For this, let me do that. Taste. Let me explain this way. Hold on. Interaction. Okay. The taste. So that is to say, when we use the beam B, we use low temperature, the preference between the beam A and the beam B. No such big difference, right? When we increase our temperature into this one, and the beam A and beam B, the taste, this is conveyed from our customer, is a big difference. So that is to say there's a big interaction between the brand of the coffee and the temperature applied. Let me say it again. These two, this is called the interaction. There's two different. For this, maybe this is the low temperature. This is low temperature. So between the beam A and beam B, this is the high temperature. So which this is a high temperature between the beam A and beam B. So yeah, you see that the effect, the main effect, they are not parallel. So that means we have interaction, something like that. Let me see that. Let's see that. Okay. Then why use DOE? Since DOE that is able to bring the process back to normal. Now back to the center. Bring the process back to the center. So this is the major objective we would like to achieve. So shift the average of process like this. We're going to change that a little bit, reduce the variation. Well, for the average of process, there's reduce the standard deviation, or the shift the average and reduce the variation simultaneously. So it could be one, it could be both, both purpose. So DOE techniques, the full factorial, totally, this is a factorial going to one of the most influential DOE technique in all worldwide. Like if I involve the 4 different factors with 16 run, 2 is the number of the level for each one with a 2 level, and totally how many factors involved? We have a 4. The factor involved. So all combinations are tested. This is called the experimental cell. No, not this is cell, called the cell, SCELL, called the cell, experimental cell. Then fractional factorial can reduce the number of trial. Okay, let me see that. Let me introduce another idea. What is a fractional factorial design? So in Chinese, we call the in Chinese, in Mandarin, called the 部分因子这里. So actually, that means we only implement a partial portion of a full factorial. Yeah, let me give you an example. For example, totally we have a 10 of, for example, we have a, for example, we have a 6, I'm sorry. We have a 6 factors. So for each factor, we have a 2 level. How many possible combination we need to run? Jiang Mingchun.
36.
36? 5, 36, 64, right?
60.
2 raised to powers to 6. 32, 64, right? Should be 64, right? Am I right? 杜嘉诺, am I correct? 杜嘉诺,
Yes.
are you there?
Yes, you are correct.
Yeah, this should be 64. However, in practice, this is sometimes, some cases, in some circumstances, they're very difficult to run all the experiment, right? It's too expensive, costs too much, too much money, too much resources we need to pay. So we need to run the full factorial like a 2. Is that possible to run the 2 raised to power, for example, 6 minus 1? Down to 32. 2 raised to power 6 minus 1. So originally we only have to run the 64. Now only have to run the 32. So that is called the fractional factorial. Only run the half. Okay, we have a 10 minutes break. So please return to the online class after this break. I see you later. Okay, we're back to here. So we're going to have a different layout. So this is like a classroom. Yes, I like that. Yeah, pretty much. No, I changed light to here, like this. Can I? No, this is, no, it doesn't seem like a classroom. No. Okay, then we have here. Okay. So is everybody back here? Is everybody back here?
Yes.
Yes, teacher.
Okay, then all the combo. So if I put, hold on, I just turn it off. I turn my line off. Hold on. Okay. So if we have a 6 process variable, then we like to run the only 1/4. So that is a 6 minus 2. So that means we only have a 16. Well, we only have to run the 16 run. So this is a 2 raised to the power 6 minus 2. This is 1/4. So if we run the half, this 6 minus 1/4. 6 minus 2 is a 1/4. Okay. Then fractional factorial can reduce the number of the experimental replication. So like this. This is a mini case, a Nissan Motor Company, the factor for this one, adhesion area, type of glue, thickness of the foam, tire, thickness of logo, amount of the pressure, and so on and so forth. The pressure application time. So this is example. So yeah, design array. So for the A factorial, you have A. So the glue stirring, this is output. This is a response variable. Effect A plus and minus. This is a high. This is a low. This is high. This is low. This is high, low, high, low. A, B, C, D. For each one, this is a total of 16. However, only run 8. Holy. So adhesion area is type of glue, thickness of foam tire, and thickness of logo. Yeah. So then performing the main effect, we can see the adhesion area. So this is a positive main effect since we have a positive slope. So we have a positive slope, means a positive effect. If we have a negative slope, it means a negative effect. Okay, so quite straightforward. So for the title good, so it doesn't seem that much. The difference, this is across horizontal. Increase from 5.5 to 5.58. This is negative. This from the negative to positive. Well, so it depends. It depends how you look at that. This is negative. This is negative. So this is a circle or logo. So step in planning an experiment. this is quite systematic procedure. So define objective, then we're going to select the response and select the factor. So once y, the x and y are determined, then how many possible factor level are chosen? Select is experimental design. Most of experimental design we can use factorial design, or we're going to see that other factorial, or this is a Takeuchi design, factorial design, Takeuchi design, or fractional factorial design. Yeah, it's a frequently used as well. And do you have any idea what kind of the other design can be used? Patricia, I'd like to comment. Yeah, Patricia. Or Shaolin would like to comment?
I don't really know.
Or Huixin, do you like to have a comment? Or Jiwei, Lin Jiwei, are you there?
Yes.
Hello.
Yes. Hello.
I cannot hear you. Jiwei.
Yes.
Hold on. I'm sorry.
Okay.
I'm sorry. I mute myself. I'm sorry. Yeah, I'm sorry.
Can you hear me?
Yes, I am now. I'm sorry.
Okay.
I'm sorry. Okay. It's only possible.
I have no idea.
No idea. And Saul, would you like to have a comment?
I don't really know.
What? No?
I don't really know.
Okay, so yeah, there's some design. Yes. Well, possible design. For example, we have a factorial. Or we can use ANOVA, analysis of variance, or this design, factorial design, ANOVA design, or we have a central compositive design, or we have a response surface design, or we have a mixture design. That's why this is particularly used in the chemical engineering, or the central compound, or the hybrid design. Yeah, there's so many, so I only give you some example. Okay, then select experimental design, run experiment, collect the data, analyze the data, and draw the conclusion. Going back to validate our objective. So then we almost there. Then no amount of experimentation can prove me right. A single experiment can prove me wrong. So yeah, that means we try to run as many experiments as possible. So, Mengyu, what do you think about my statement? Run as many experiment as possible. Is any flaw, or is any problem with this statement?
I think according to our text, PPT, and No amount of experimentation can prove me right, but you say run as many experiments as possible. I think that is sometimes waste of time and materials.
Yeah, that's
so,
cool. Yeah, that's cool. So we have a limited. Cool, very cool, very cool. Thank you, Mong. Limited resources. So we have to run a reasonable amount of experiments. Then we have give us some level, at least some other level of confidence, so we can get the result and trust the result. However, only one can prove us wrong, since as long as we find we run a single experiment, put us wrong. So we're going to think of is any particular experimental procedure it is mistakenly designed or mistakenly planned. So science can only ascertain what is, but not what should be. And outside its domain, outside its domain, domain value judgment of all kinds of remain necessary. That means science ascertains something should be true, but not should be. Ascertain what is true, but not should be true. And outside its domain value judgment of all kinds of the remain, all kinds of the different judgments should be necessary, remain necessary. Why? Since environment is changing, right? Environment changing. They're going to be different from day to day, maybe from week to week, maybe from hour to hour. So how can you prove? You experimental value throughout the day, throughout the year, throughout the week, or throughout the month? No way. So so that finally we achieved the control phase. So control phase related to Six Sigma. So conformation improvement and conformation, you solve the practical problem, benefit validation. So always about benefit validation by dollar sign. In terms of dollar sign, evaluation in terms of dollar sign. Then buy into the control plan, quality plan implementation, procedure change, system change, statistical process control. There's the SPC chart. Statistical process control. Yeah. And mistake proving the process is like a poke-yake in the poke-yake. This is called the error proof. Error proof method. And the closure document. So put in the ISO. This international standard organization called ISO. So finally, we have a audit process, the accreditation, accreditation system, like a ISO or like a Dell or like a or SGAs, or the scope in the next project. So control phase, how to create control plan. Select the cost variable, the proven the vital plan, the vital field, and define the control plan. The 5W and the why, how, and when, or something like that. The optimal range, the validate the control plan, observe the why. Finally, implement document control plan. Audit control plan, finally model performance matrix. So performance matrix what is the maybe we're going to evaluate the output matrix in terms of the yield. It could be the defect rate or the throughput. I'm sorry, throughput or productivity or OEE. I'm sorry, overall equipment evaluation. They call the OEE, typically utilized by the semiconductor fab. Something else? We like to evaluate our throughput. Yeah, the monitor performance matrix. Is there any other performance matrix? So I just give you so many examples. Is anything else you can think of? Somebody? Yeah, like 江明川 what do you think? What do you think? Yeah.
I don't know.
Productivity output. Yeah, I give you so many examples. Can you think of the different one? Give me one more example. Or Sao, do you have any idea?
I'm thinking.
Yeah, okay. Mengyu, from your domain, you are from the material science.
Yeah, but teacher, can you say it again?
Okay,
Sorry.
I rephrase again things like this. Like this, we try to monitor performance matrix. How can we maintain the status quo? Maintain the quality output, or we're going to that means is any particular matrix that can be used for the performance monitoring and the performance evaluation? What kind of index that can be used to determine the process is good or not? Like this, we have a yield, process yield, defect rate, throughput, productivity, OEE. Anything else? Yeah, Mengyu, you are on the street, right? So I hear some car is rolling after you. No? Are
Me?
you at home? So are you at home or somewhere else, or are you in 7-Eleven or?
Oh, I'm in my room.
Okay, in your room. All right. So.
I think flow rate is.
Oh, flow rate. Can you explain what kind of flow rate you are mentioning?
Let's say semiconductor and inside maybe have some flows.
Oh, okay, I saw. Okay, I understand. Cycle time. Cool. Cycle time. Okay, from the raw material coming to the fab and come out. So what is the cycle time? So we'd like to reduce. So cycle time reduction. That's cool. Then Jiang Mingchuan, anything else? Cool. Or Jiwei?
Maybe lifetime.
Lifetime, okay. Yeah, cycle time for the product, cool. Product lifetime. Lifetime, that's cool. Yeah, that's good. They're really good. Product lifetime. Anything else? Saul?
KPI.
Hello.
Hello.
Yeah. What do you say?
KPI.
KPI. Oh yeah. Okay. The key performance indices. Okay, cool. I think we have good enough. Then back to here. Then finally, control phase, the control plan. We have a 7 tool affinity diagram, tree diagram, process decision diagram, matrix diagram, interrelationship, prioritization, activity network diagram. So yeah, you can punch in those into the wiki. So there's some explanation. So I won't want to get too much details. Statistical process control uses various types of control chart, like this is the variable control chart, like a S, R, or X bar, the attribute control chart, MPPCU, and so on and so forth. And additional variable control chart like EWMA or pre-control chart or the QSUM. QSUM. So cumulative sum. This is known as a QSUM chart. Then I think I almost finished this chapter. So yeah, let me just go through very quickly affinity diagram. So the characteristic of the affinity diagram is organizing idea into meaningful categories. This is like a quite conceptual modeling. The data reduction, large number of quality or quantity input, quality input into major dimensions or categories. So use a method to, this kind of method to make easier for users, like innovation, like this. This is product management, overall goal of the software, knowledge of the competitors. This is from outside. So this is the 5 forces. Analysis. So some forces come inside organization, something comes from outside the organization. So the product design, product management for innovation for the new product, like the COVID-19, going to have different mask design with a different sanitization design, and product management, product design, and supervision. So yeah, this is a quite easy, straightforward method for user output, support, intuitive answer, and direct organization. So this is affinity diagram. First of all, the idea, benchmark with a competitor. What is the product design? What is the product management? Finally, what kind of the supervision procedure? So like the matrix diagram is like pretty like a QFD. So what's the relationship matrix? This is about what's about the horizontally about how. So the 5, this is a number that means high importance. The 3, yeah, indicating mediocre, quite average. 1 is low. The multiple, so going to so the rank for this one, let me see that. Okay, is the relationship about what arrive at the scheduled time, quite important. 5, arrive with the proper equipment, yeah, something need to come with that. 4, dress properly. 4, deliver via correct mode. 2, take back to room properly. 4. So this is the what we need to do and how. This is like the patient schedule, and this is attendant assign, attendant arrive, and obtain equipment, and the transport patient. Actually, the example this referred to hospitality. No, hospital. Provide therapy, notify or return, and attend and assign, attend and arrive, and the patient return. So yeah, this is a relationship. Finally, the importance score like this. So for the patient, so something, how can we do? So this is something we need to do that. How? So for this, the patient schedule. Once while the patient arrived, the front desk of the hospital, there's so many things we need to do. The patient schedule. There's a 1, 2, 3, 4, 5 different things need to do. According to their item and according to their corresponding importance or score. We'll multiply them together. This is 25 plus 8. 25. This is 0. This is 0, 6, 11. So total 25, 8, and 14 total. Sum up to 39, right? This is 5, 5, 20, the 25, the other 0, so the score. So according to the total score, we're going to rank it. So from the highest to lowest, the 1, 2, 3, 3, and so on and so forth. So this is a matrix diagram. Okay, based upon this, going to create a matrix. According to the matrix and importance multiplied together for each, how can be done for each item with the corresponding importance score, and we rank it from the highest to lowest. Okay, then, so this is a combination ID matrix diagram. This is a feature make existing product faster. So this is strong inference 3, this is 1. So we use a different symbol in the circle. This is like the Ghostbuster, like a Ghostbuster diagram. This is a circle, triangle, something like that, and they use that. Okay, only for your reference. So many tools available in Six Sigma. Control plane 6 Sigma, Sigma control 7 tools. So yeah, so I mentioned this already. Then this is how do we select the correct control chart, like this, SPC. So yeah, let me just go, let me go with it one by one. First of all, we need to determine this is an attribute or variable, okay? If it's an attribute, we're going to focus on the defects or defectives. About the defect, so opportunity area, constraint, a sample to sample. If yeah, so going to use a C or mu, and then if only take individually, so going to use a U. So for the defect type, we like to just calculate the fractional proportion of the defective. We're going to the P chart or MP chart. So size of the subgrouping constant, yes. This constant we use a P chart, MP chart. If it is not, use a P chart. And so this is for the attribute control chart on the left. On the right, if the variable is individual, is normally distributed, yes, then we use the X and R chart. And it is, we have a batches or group of the measurement or subgrouping. Then interest in the sudden mean change, yes. The big change, we use the X and R. If no, it's a sudden change, we like to use a moving average, Q-sum, or EWMA. So this is on the right. This is for the variable control chart. Then there's some example, right? And I just enlarge it. So the X chart. So upper control limit and the lower control limit. And for the P chart. Things for samples to sample, they have a different sample size for difference sum. So different sample size is going to have different standard error. A different standard error of the fractional proportion due to the different sizes. So like this, you can see the jigsaw pattern of that, since the lower bound can be negative, so P is a proportion, it can be negative. The minimum value is 0. So P cannot be negative. P cannot be negative, no way. So the lower bound gotta be greater than or equal to 0. So see that. And then this X bar chart for serial. So if 1, you can see that. So from the sample 1 to sample 19 behave well. Suddenly up to 20, there's a point extrapolate or just product outside the lower control limit. So this is signal. This is a signal or process abnormality. So call this, yeah. Okay, then pre-control. The additional variable-based tool called a pre-control. This is an algorithm for control based on tolerance, called the tolerance design, related to the tolerance design. This is the third phase of the Taguchi method, tolerance design. In Taguchi's quality engineering. Okay. So we assume the production process with a measurable adjustable quality characteristics that vary from batch to batch, not equivalent to SBC process known to be capable of meeting tolerance and assured that it does so. So SBC use always before pre-control is applied. So then process qualified by taking consecutive sample, the several individual measurement, until 5 in a row for within the central zone. So called this is a pre-control. So before we just excuse me. Before we ramp up, we need a pre-control. In this case, we try 5 consecutive fall in the central zone before 2 fall in the cautionary action taken if the 2 sample in the the causal zone, the color code. So yeah, like this is tolerance. The lower the tolerance limit, yeah, this is red zone. This is red zone. In between, this is nominal in the middle, nominal dimension. This is pre-control. This is the pre-control, and this is reference line of the pre-control. So within that, we have a green zone. Outside the green zone, we have a yellow zone. This is called something you need to be cautious. So that is to say the SBC use always before the pre-control is applied. So during the pre-control, we still use this. Like we have a control limit or warning limit. Excuse me. Yes, WARM. warning limits. Then outside that, definitely this is not satisfactory. However, in the yellow row, so process qualified by taking considered sample individual until 5 in the row, 4 in the central row. Before 2, 4 in the cautionary, this is a cautionary. Then action taken is the 2 sample in the red zone, color code. Okay, then the 2 common causes chart, EWMA. So it is, excuse me. So I'll be back in a minute. I'm sorry. So I'm back, I'm sorry. So this is the mean of the automatic manufacturing process drift because of the inherent process factor. So SPC consider process which is considered static. So yeah, we use the EWMA and action are placed on the chart. So going to rely on the previous observation and put on the weighted, no, exponential weighted on the past observation. So process mean tackled by the EWMA, the benefit used when process drifting away. Yeah, IFT drifting away from center. If it is a drifting away from center, we try to use the EWMA instead of the Shuha chart. Used to develop procedure for dynamic process control. So if the process is changing from time to time, so we better use the EWMA like this. So this is YT plus sigma YT minus. So sigma is between 0 and 1. So this is EWMA equation. Then okay, so I do not get into too much detail. And anything else, I think. So this is EWMA. So you can see that. So the stand, so temperature, so something. This is EWMA. There is a more sensitive. So quite sensitive. It is a drifting away, change from time to time. You can see that the tracking capability is quite good. This is so EWMA form. So EWMA chart is more responsive than X bar chart. Yeah, this is a much more sensitive. So project closure. So we're almost there. So going to wrap up this slide. Then so improvement fully implemented and process re-baseline. So yeah, when we done, we need to report our conclusion for top management to close the project. And then that will going to be another brand new starting for another new project. So quality plan and the control procedure institutionalized and owner of the process fully trained and running the process throughout and learn from taking charge of that. So any required document done. So yeah, we get document done by using the ISO. History binder completed, put in the archive, the closure overshoot sign, and the scorecard developed, and the characteristic improve, and the reporting the method defined. What kind of method defined? So yeah, Motorola, this is return of investment between 87 and 94. Yeah, there's some performance by applying the Six Sigma alias signal. Yeah, there's something good about application of the Six Sigma. This is GG return of the 1 billion. This is, yeah, there's something only for your references. So this is a bibliography. So yeah, I wrap up this wrap up Six Sigma over the past 3 weeks. So we're going to have a test. Hold on. So we are going to have the midterm. Midterm next week. So then let me see that. This is a 2-hour. It's a 2-hour test starting from next week from 1 to 3 p.m. So I'm going to send the test. I'm going to send the test via line, okay, to all of you. So everybody should turn your camera on to let me see you. I need to monitor one by one, so I need to see everyone. So please turn on your camera. I need to confirm all the tests is done individually. Is that clear? Hello, answer me. Is that clear?
Yes, teacher.
And after you've done that, you fill your answer. Fill your answer in your Word and change the file name of Word into your name. Is that clear? And convert your answer in Word into PDF. First of all, you change your file name into your name and convert that Word file into PDF. Is that clear?
Yes.
And then send your PDF back to me via the email. ORSFN_NTUTPW. Okay, so you need to turn on the camera all the time. Do not turn it off. So I will check one by one. So you need to send out your PDF by 3 p.m. So I will check this. I will check the timestamp of your email. So this is open, no open everything. So it's just no, it's just want to. However, things that you turn on your camera. Let me see you. How can you answer those questions? That's it. This is the only requirement I put on you. Otherwise, so you can check all the resources you have. And all the answer. All the answers should be put on English. Is that clear?
Yes, teacher.
Okay, is there any questions so far? I'm gonna stop here. I think that's going to be the day. Is there any question? All the process online? Yeah, of course, all the process online. Since I think pandemic will will not end. No way. The pandemic will last at least 1 month. I don't believe Taiwan has the capability to finish within 2 weeks. It's only slogan to comfort our, no, this is comfort our, or ease our pain. Actually, it is not. Question will be online. No online. Come on. The question, all the question in the Word file. Is that clear? I send you the Word file. You need to fill your answer into the Word. Okay, Zhang Yichun, is that clear to you?
Yes, teacher.
And Meng Yu, are you clear? All the process.
Yes.
Yeah, then so I send the Word, and you just open the Word, you download the Word, and on your computer, you just work on your answer. However, you need to turn on your camera. That's it. This is my request, only request. Any question? Any question? No? Okay, thank you. And let's call it a day. And so just